Welcome back, class. Today we are going to start our discussion of kinetics. So the field of chemical kinetics is one that's extremely important in our study of chemical reactions. Now, when we think about kinetics, right, we think about motion and movement of molecules and atoms in general. Now, chemical kinetics, when we apply it to the study of reactions, is looking at different things that affect the rate at which a chemical reaction occurs. In other words, how fast that reaction goes. Now, we're going to look at generally about kinetics. We're going to look at some different aspects of kinetics, like what things can affect the kinetics, because there are things we can change that'll make a reaction go faster and slower. So we'll look at concentration, temperature, for example, as things that might affect how fast a reaction goes. Now, we're also going to look at some other topics that deal with or that are involved with the study of the kinetics of a reaction. Now, the speed of a chemical reaction is called its reaction rate. And so, in other words, the rate of the reaction, when we're doing that, we're talking about the speed or how fast the reaction goes. Now, mathematically, right, it's a measure of how fast the reaction makes products or uses up reactants. So we can look at it either based on observation of the products that are produced or the reactions that are being used. Now, you're probably familiar with rates in general. And if you're not, let me remind you, right, that a rate is simply how much something changes, so how much a quantity changes in a given period of time. Probably the most familiar one is something like speed, right? When we talk about how fast our cars are going, we look at the speed that we're traveling. In other words, how many miles that we've covered in a given period of time, so miles per hour. It's the same idea for a chemical reaction, but we're looking at how much the concentration has changed over a given period of time. And so we're going to look at the concentration change, again, either of reactants, which are going to be decreasing, or we can look at the product concentration increasing over some period of time. So this is going to be our standard way that we think about the rate of a chemical reaction. Now, if we observe the reaction, we can create a graph. Now, you'll see these graphs throughout the book and in different aspects when we plot the concentration versus time. And we can plot how the concentration of a reactant, the concentration of a product over time. So if we look at our graph here, we have two plots. We have first the plot of the production of HI over time. That's shown in red here. And we have a graph of the use or the decrease in the amount of H2, one of our reactants, over time. Notice that the product concentration goes up over time, as you would expect, and the reactant concentration goes down over time, as you would expect. So this is the reaction that we're looking at. So the reaction of hydrogen plus iodine to give two equivalents of HI, right? So in other words, we would read this reaction as 1 mole of hydrogen gas reacts with 1 mole of iodine gas to give us 2 moles of HI gas. Now, one thing to note here is the curves do not look identical, right? Of course, one's increasing, one's decreasing, but beyond that, they look different. They have different slopes and so forth. And that comes from the idea, or that comes from the fact that we have different coefficients in our reaction. So, in other words, every time we use up 1 mole of H2, we produce twice as much, or 2 moles of HI. So, the stoichiometry of the reaction is also going to be shown in these graphs, or it's going to be obvious from looking at the graphs. So we can see that the red curve here is increasing twice as fast as the green curve is decreasing. So coefficients are important. Now, how do we look at the rate? So as I said, we're typically going to express the rate of a chemical reaction as the change. So remember our delta sign, it means change in. The change in the concentration of some material over some change in time. Now, a couple things I'll point out here. So this example uses hydrogen. Now, first, remember that when we enclose something in brackets, right, like this, when we use this kind of symbolism, what that's referring to is the molarity. So anytime as we go through not only kinetics, but other topics later on in the course, right, we want to remember that when we put something in brackets there, we're indicating that that's the molarity of it. Also, I'll point out the negative sign here. We have a negative sign here because we're looking at a reactant, and that reactant is decreasing. So if I go and do my math here, now notice when I do my change, it's final minus initial, right? Anytime we calculate a delta, right, it's always the final minus the initial. So we have our concentration at time 2 minus our concentration at times 1. And again, we have our final time minus our initial time. So we get our change in time. Now, we want these to be positive, right? We gotta have positive rates, right? The reaction is not going at a negative rate. So in order to do that, right, the change in concentration of a reactant is going to be negative. Okay? So in other words, the value of T2 is going to be smaller than the value of T1 because the concentration is decreasing. And so if we just calculated the change in concentration here, we'd get a negative number. So anytime we're dealing with a reactant, we have a negative sign in front of here so that our rate is positive. So we've got to keep in mind, if we're using reactants, we're going to have that negative sign there when we express the rate. If we're looking at a product, right, it would be a positive sign, right? There's no need for the negative sign there. Now, in some reactions, right, as we just saw, right, the coefficients are not all the same, right? It's very rare that we find a reaction where everything is a coefficient of 1. Now, it does happen, or same coefficient, right? So typically we have different coefficients. So, for example, in the reaction we're looking at, right, we can see that 1 mole of H2 reacts with 1 mole of I2 to give 2 moles of HI. Now, if we think about that, then if I calculated the rate of change using H2, right, I would get one number. But if I did that using HI, right, I would get a different number because it's changing twice as fast, right? And so we have to think about that, and we have to account for that because there is only one reaction rate, right? It doesn't matter what we study, we shouldn't get a different rate for the reaction. The reaction is moving at some speed, right? That's like saying, you know, your car is moving at different speeds depending on how you look at that speed, right? No, the car is moving at a certain speed, no matter how we look at it. And the same thing, the reaction is changing, is producing, you know, at a certain rate, no matter how we choose to study it. So we have to account for it. It's very simple, right? We simply need to multiply by 1 over the coefficient in our reaction, right? And so that will standardize the rate that we get so that it's always the same. So in other words, if I'm going to use HI, I need to multiply by 1/2, right? Whereas if I'm using H2, I just multiply by 1 over 1 or 1. So that's going to ensure that we always get the same rate no matter what we choose to study experimentally. So if we look back at that graph and we do some numbers. So we're going to calculate what's called the instantaneous rate Now, the instantaneous rate is the rate at any given time during the reaction. So the way that we would get that is that we would look at our rate curve. So we look at our either our green curve here for H2 or our red curve for HI, and we pick a point. So in our example here, we're going to pick 50 seconds, and we draw a tangent line to that point on the graph. And then we measure the slope of that tangent line, essentially, right? We measure the change in concentration versus the change in time of that particular tangent line. So let's say at 50 seconds, we draw this tangent line here to the H2 rate curve. And we extend it out, and so we measure our rise and our run. We get our change in concentration, again, as a negative 0.28, right? It's going to be a negative change if we do final minus initial. And the time here is 40 seconds that we've drawn our tangent line. So we have our change in concentration over the change in time. We get an instantaneous rate of 0.007. Notice our units, molarity per second. So it's changing by 0.007 molarity per second, or is that rate of change. Notice the negative sign here because we're looking at a reactant. And so those negative signs will cancel out. Now, if we do the same calculation, or we measure the rate at the same point using HI, so we're looking at the appearance of HI here. So we take our 50 seconds, we draw a tangent line, and we measure the slope of that curve. Now, notice that slope is going to be different, right? Because of the different stoichiometry that we have. So if I measure that, we get a change of positive 0.56. Notice the change is twice as much as you would expect, but over the same time period, right? Because we're producing twice as much HI as we're losing H2 because of the stoichiometry of the reaction. So if I just did that, I would get a rate that was twice as much. So remember, that's why we have to multiply by 1 over the coefficient. And so we get, not surprising, we get the same rate if we look at the change in HI at that same point, as we should, right? The rate of the reaction at 50 seconds is 0.007 molarity per second. Okay, so that's a little bit about instantaneous rate. Now, in practicality, instantaneous rates are great, but you need to generate a curve to do it, and sometimes they're not the most useful rate, right? A lot of times we don't necessarily need to know the rate at a given specific time, but we want to know maybe, what the rate of the reaction is over the course of, some time period. So another approach that you can use is what we call average rates. So as a reminder, right, the instantaneous rate is the change in concentration at any one particular time, right? In other words, the slope of that tangent line that we went through that example for. Now, the average rate is the change in concentration over any particular time period. So we can pick, these 10 seconds of the reaction, these 30 seconds of the reaction, this minute, right? We could take it over the entirety of the reaction, whatever it might be, right? It's the average rate of change over that time period that we're looking at. And so this is, if you want to think about it mathematically, right? We're doing a linear approximation of that curve, right? Now, what we're really going to focus on is how we calculate that. So basically, we're going to look at the concentration at the beginning of our time period, the concentration at the end of our time period, and we're going to divide by whatever the time period was. And we'll look at an example here in a second. Now, of course, the larger the time interval, the more the average rate will deviate from a given instantaneous rate. So if we look at very short time periods, it's going to be very close to the instantaneous rate at some time within that time period. But as we expand over a larger period, then the average rate is going to be much more different than the instantaneous rate at any given time during the reaction. Because what we notice from that curve, right, is the rate is not constant. So if we look back at that, look at the shape of the curve, right? It starts out very steep, whether we look at HI here or H2 here, right? It starts out relatively steep. But then over time, it flattens out, right? It becomes less steep as we get up here or get down here, right? So in other words, the rate is changing, right? The rate is not constant. That's why we don't see a linear, right? That's why we don't see a straight line. So if we take an average rate over a long period of time, it's building in that very fast rate at the beginning, that slower rate as we get toward the end. So the average is going to be, again, it's going to deviate from the instantaneous at any given time. So instantaneous rate, average rate. So if we look at rate data, so this might be rate data that you would collect, right? So you measure, every 10 seconds here, we're measuring the concentration of H2 by some means, right? And so we can pick, right? We can pick any two numbers here, and we can calculate the change in that concentration over any particular time period. So on this graph, they've measured the rate every 10 seconds, or they've measured the rate of the reaction every 10 seconds. So if we take the first 10 seconds, right, it changes by, the difference here over 10 seconds, and you get a rate of 0.0018. Notice as we go down here, the rate gets slower and slower. So what we can say is the rate decreases over time. And this is true for almost all reactions, right? The rate gets slower over time. Now, why is that? Well, it's not too difficult an explanation, right? Because the concentration of the reactants will decrease over time, and as there's less and less reactants around, the molecules are going to collide less and less frequently, so you're going to get less and less reaction. And so as your concentration of reactants decreases, the rate of your reaction is going to go down. Now, at some point, the reaction will stop because the reactants run out, or, as we'll talk about in upcoming chapters, the reaction has reached an equilibrium point. Now, of course, we have to be able to measure the rate of the reaction. Now, there are many ways to measure the rate of the reaction. In the book, it talks about looking at the reaction of glucose and fructose, right, from sucrose, right? And those studies were done quite a long time ago using plain polarized light, right? So how did the materials interact with polarized light? They interact differently, so you could measure, how much of particular was there by looking at the behavior of polarized light. Now, today, a very common method to measure is spectroscopy, or using a spectrometer, which, if you remember back to Chem 1, right, this is what we did when we looked at bromophenol blue, and we measured the concentration by looking at the absorbance, right? This is particularly useful, right, if you have one of your materials is colored, right? You can use visible light to do it. But using a spectrometer is a useful way to measure the concentration at different times during the reaction to generate the data like we just saw. And you could plot that data to give you a concentration over time kind of curve, and then look at the rates. Now, spectrometry is particularly useful for reactions that are relatively fast. So you can start the reaction and just measure it in real time, right? So you can measure how the concentration changes by looking at how the absorbance changes over time. Now, some reactions you can set up in a way where we don't even need a spectrometer, right? We can just observe the reaction using a stopwatch, and we can look for some change visually in the reaction, like a color change, for example, and we can measure the rate that way. And that's what we're going to be doing in lab. We're going to set up a reaction in a specific way so that we get a very particular color change when the reaction is done. And so we don't need fancy equipment necessarily, but we can use all kinds of different techniques to look at the rate, right? Anything that will allow us to know the concentration over time. So reactions that produce gas, we can use pressure measurements, and we can relate that pressure to how much gas we've produced, etc. Now, some reactions are quite slow, though, and maybe spectrometry is not the best way to do it because we're looking at such a long period of time. So if we have slow reactions, we could still use spectroscopy, but we can use something called an aliquot method, where we don't measure the reaction as it's occurring, but we take samples of the reaction at different time periods. So, every, say 2 minutes or 5 minutes or whatever period of time we need, we take a sample of the reaction and we measure it somehow. So you could measure that using spectroscopy still. You can use other chemical techniques like gas chromatography or lots of other methods as well to get concentration at those particular time points. So bottom line is there's many ways that we can measure or get data that can be used to give us kinetics, right? So really anything that allow us to measure the concentration of a given material at different time points. All right, so that brings this video to a close. In the upcoming videos, we'll look at equations for the rate. We'll look at things like catalyst. We'll look at things like the mechanism of reactions. So this in the upcoming videos, we'll talk more and more about different aspects of the kinetics of reactions.